Hi, and welcome to SageMaker Fridays. I'm Aaron Sinstack, and I'm a machine learning solutions architect. And today we're going to talk about SageMaker geospatial capabilities. I'm joined today by my colleague, Zhang, and I'll let him introduce himself.
Hello, everyone. My name is Xiongzhou. I'm thrilled to be joining you today for this exciting webinar. I'm a senior applied scientist at AWS, where I specialize in building machine learning models with geospatial data. Today, I'm especially excited to be co-hosting this webinar with my colleague, Aaron. Together, we will be discussing some of the features we build in SageMaker Geospatial, as well as sharing our thoughts and insights on the topic.
Awesome. Thanks, Zhang. As Zhang mentioned, we're going to focus on SageMaker Geospatial. SageMaker Geospatial was announced very first time at reInvent 2020. This was just a few months ago. We're going to dive in today and show you how to use the geospatial capabilities. Let's first talk about the agenda. So for the agenda today, we're going to talk about the capabilities that we released for SageMaker Geospatial. We'll also provide some motivation on why geospatial capabilities are needed with machine learning and why they're hard today. We're going to walk through two different demos, one around deforestation and how we can monitor that using open satellite data. We're going to do a second demo also where we monitor the snowpack, the glacial coverage of a mountain. And we're going to show how those two analyses are a bit different and the capabilities that we have within SageMaker Geospatial. At the end, we'll recap what we walked through and we'll provide you some links on how to get started. Let's dive in. So first of all, what is geospatial data? Geospatial data roughly falls into two camps. Number one, raster data. And raster data is pixelated or gridded data where each pixel is associated with a specific geographical location. Think about this as images, right? That's my mental model is satellite images where each pixel of an image is located to a geographical location. This could be elevation. It could be a category such as land use. Is this water, desert area, urban area? And that's raster images. So raster, again, is pixel-based gridded data. We also support vector data. So what is vector data? Vector data is mapping data. It's attributes that are applied to the Earth's surface. So think of this as points of interest, GPS traces, maybe a road network. And typically these terms of raster and vector might not be common to the data science community that's used to working with computer vision applications. Again, raster data is satellite images and vector data is maps and GPS traces. We're going to show you how to get started with this data today. So what are some challenges of working with geospatial data with machine learning today? Well, first of all, accessing high quality data can be an issue. You might have multiple data sources or vendors. Some of this data might be proprietary or commercial licensed. Additionally, the images that we might be using are much larger than images that you might be used to with computer vision applications. So how we approach the problem is just a little bit different. The tools that we need to approach the problem are a little bit different. And many times we have specialized tools for geospatial analysis. So how do we use those in concert with our machine learning tools? We might want to integrate geospatial analysis within a machine learning operations pipeline, an ML ops pipeline, where this type of model, this type of analysis is reproducible and automated. And then lastly, data scientists aren't always experts in geospatial data, and conversely, geospatial analysts are not experts in machine learning, right? So the learning curve for both of these topics can be steep, and it's our goal today to show you how to get over that learning curve, whether you're a data scientist coming to geospatial data or a geospatial analyst coming to data science with SageMaker. So let's address that first challenge about how do we access geospatial data sources? Well, with SageMaker Geospatial capabilities, we've announced 3 different data sources that we support out of the box. Number one is Landsat 8 dataset. Number 2 is Sentinel-2 data. And then the third is OpenStreetMap. These are all raster data sets. that you can use with SageMaker Geospatial. These are different satellite constellations that have been hosted on AWS for a number of years, but now we're making it easier to query data, to filter data, and find the area of interest that you're interested in for your geospatial analysis. Now, you might be thinking, well, what if I have license data already? Can I bring that to SageMaker Geospatial? Absolutely. So we've already announced that we support bringing commercially licensed data from Planet Labs into SageMaker Geospatial. We've had an announcement on that a few months ago. And additionally, if you have other data sets, maybe they're proprietary data sets or licensed data, you can also bring that in for use within SageMaker Geospatial. So SageMaker Geospatial helps address those pain points, accessing high quality data. Also, how do we use pre-trained models? Right? Many times the analysis that we want to do as a data scientist using geospatial data is very common. It's common to the geospatial analyst, and this might be analysis like land use segmentation. So what is the category of land use for the image that we're looking at? We might also think about object detection. We might think about cloud masking, cloud filtering, cloud identification, or simple equations where we want to implement a band index. And we're going to show you how to do that with one of our examples today, where many of these data sets are not just the visual bands that we might be used to dealing with of a red, green, and blue channel, but they're multispectral images where they could have up to 12 or 15 different bands. And how we do the ratios of those bands and equations of those bands can give us additional insights into our data. And then lastly, how do we interact with this data? I already mentioned that the data sets are large. Are there tools now within SageMaker Geospatial to visualize the data set? We can apply not only the underlying map, but we can overlay that with true color images and the analysis that we're executing with machine learning built-in models. We see our customers using geospatial analysis for a number of different use cases. Customers within the public sector are using geospatial analysis to support risk and insurance claims. So how do you determine if your location is at risk based off of natural disasters and the impact that natural disasters might cause? How do we track construction projects from space and monitor those as they expand? We also see demand in retail space as well. Imagine you're going to open a new location, a new store. Where do you want to place that store? Many times geospatial analysis is at the heart of that decision. Where are customers moving to and from? Where are competitors moving to and from? And where are the locations that are going to be best for your retail application? Lots of different applications for geospatial analysis. Additionally, geospatial data is everywhere. It's everywhere even if we don't know about it. And that's, again, that raster data and the vector data that are both supported by SageMaker Geospatial. I now want to move into a demo, and just to motivate that demo a bit, we're going to look at deforestation. So up to 15 billion trees are now being cut down every year across the world, which is not sustainable. It's not sustainable for wildlife, for people, or for climate change. Forests have an impact on not only the rainfall patterns, but on the soil quality and flood prevention as well. Additionally, millions of people rely directly on forests as their home for making a living. Today, we want to show how we can monitor the area of dense forest through geospatial analysis. How does that change as a function of time? As we look over time, are we seeing that the deforested area is increasing, staying the same, or decreasing? We can use visual images. We can use raster data and multispectral images to help aid in this analysis, and we'll show you how next. So we're going to jump over to the demo. All right, now we're going to jump over to the demo for the deforestation example. And we're going to start here in SageMaker Studio. So SageMaker Studio, you can see that this is the new user interface. That this user interface was also announced at the reInvent conference of 2022. It's a cleaned up user interface, and this is SageMaker Studio with geospatial capabilities that we're showing. Before we get started, I just want to call out a couple additional pieces here. You'll notice that we're operating here using the Geospatial 1.0 kernel. There's a number of pre-built kernels that are available within SageMaker Studio, and if we select this kernel, we can see that there are other images available. As part of the SageMaker geospatial capabilities, we also released this geospatial kernel. This allows for you to get started quickly. It comes pre-packaged with popular geospatial Python libraries for you to use out of the box. Now you might think, well, do I have to use this? Absolutely not. Right? You can manage your own kernel with your own packages. This is merely a convenience. We're going to be using this kernel today and using the pre-packaged libraries that are part of the Geospatial 1.0 kernel. All right, so to get started with geospatial capabilities, there's a couple of things that we need to do. First of all, we need to make sure that our identity and access management role has the capabilities to be able to call these APIs within SageMaker Geospatial. So we've given an example here of how to update your role with those capabilities. We also need to set up SageMaker. When I think about approaching these problems in SageMaker, it's a lot of times I think about almost like a cooking recipe, where no matter the type of analysis that I'm doing, it's almost the same thing over and over. The underlying ingredients might change just a bit, but it's a repeatable recipe. So we first need to configure SageMaker. Then we're going to look for data. The third piece is we're going to be looking for what type of operation or model do we want to apply to that data. Then we're going to look at how do we export the data to be able to read it into memory, to do additional analysis within the notebook. Right? That same analysis is going to be consistent through both demos today. So let's start with that first one. We're going to set up SageMaker geospatial capabilities. We're just going to import our libraries that we're going to be using later in the notebook. And we're also going to instantiate our SageMaker session, get our execution role, and create the SageMaker client. Now, once we have that set up, when I start with geospatial analysis, I think about three things. I think about what's the area of interest, like the latitude and longitude location that I'm interested in analyzing. So here we're going to have coordinates that cover a location of interest in Brazil. The second piece is what's the time frame? What's the time range that I want to cover this analysis? So here we're looking between January 1st of 2020 all the way to September 1st of 2022. We're almost 3 years of analysis. And then the third piece is with data filtering. What's the maximum amount of cloud coverage that I want to allow for this filter? And here, I do not want to have clouds in my images, so I'm setting the maximum cloud filter to 1%.
Hey, Aaron, you mentioned there are multiple data sets provided by SageMaker Geospatial. For this analysis, how do I know which data set to search from?
Yeah, great question. So it's really going to depend on the analysis that you're trying to do. So I mentioned earlier that we have Landsat and Sentinel-2 data sets that are available. The instruments that were carried on those satellite constellations are just a bit different, right? So some have different spatial resolutions, some have different multispectral bands. So you need to think about what is the analysis that you're trying to do. For example, if you're going to use thermal analysis, you're going to want to use the Landsat data set. And then if you want to use higher resolution images in the visual bands, you might want to use Sentinel-2 that has up to 10 meters per pixel spatial resolution. So that's how I think about it. Additionally, the time range that those two data sets covers is just a bit different as well. So the Landsat data set goes back a little bit further than the Sentinel-2 data set that we have available. Today, in this example, we're going to be using Sentinel-2.
All right, thank you.
Sure. By the way, too, I can list out what data is available by just using this list raster data collections, and I can see that I have both Landsat and the Sentinel-2 data set here available. We also have the description and this unique identifier. If you're new to AWS, this is a unique identifier within AWS. We refer to this as the ARN.
That's convenient.
Yeah, it's very convenient. So we're going to use that ARN. I want to use the Sentinel-2 ARN. And I want to search. So I have this location, I have a time range and a max filter. Now I want to search what data is available that meets those requirements, that location, that time filter, and the maximum cloud. So here I have a property filter for cloud coverage. We're going to do a search raster data collection, and we'll print out the results from that operation. And here we can see these are the URLs of the true color images for that operation. And we can see that there is data that's available that meets that, not only the coverage, but also the time range and the cloud filter. And you can see here that we have 25 different images that are going to meet that data. So this is a good sanity check when you're first starting. Is there data available that meets my requirements? We see that we have 25 images here, so we can get started. A lot of times I like to download one of those images just to get a sense of what that looks like, making sure that it does cover the region that I'm interested in. And that's what I'm doing here. So you can see this true color image of the location of interest. And this is a TIFF image. You can see there's minimal cloud cover here on this image.
Hey, Aaron, what are the units on that plot? Like 10,000 number.
Oh, good question. These are pixels. So, and each pixel in this image is 10 meters. So this is actually 100 kilometers by 100 kilometers patch. And it's actually quite a large image. So if you think of traditional images might be between 1 megapixel to maybe 10 or 12 megapixels. This is actually 10,980 pixels by 10,980 pixels. This represents over 120 million pixels in this single image. Plus we have 3 channels. So lots of information. These data, this type of image is going to be much larger than a traditional image that you might be used to. For example, this image is over 300 megabytes.
Oh, that's a big image. I'm wondering how you can process such a big image.
Yeah, good question. We're gonna use SageMaker Geospatial to process it. I'm not gonna process this myself. We found the data, and now that's what we want to do is we want to process it. So we want to calculate here deforestation as a function of time. And to calculate deforestation, we're going to use something that's known as the normalized difference vegetation index. This is using one of the spectral bands, actually 2 of the spectral bands from the Sentinel-2 data set, the red band and the near IR band. So we can look at the difference of those 2 bands and normalize that as well to get a sense for how dense is the vegetation in this area of interest that we're covering. This is normalized, so it's between -1 and +1. Dense forest is going to be between 0.4 and 1.0. Like arid urban environments are going to be near -1. So we can use this index to tell where is the dense forest located, and we can threshold the index to find that area, and we'll show you how to do that next. Okay, so we still don't have our data. We found that there's data available, but we haven't calculated this vegetation index. So we're going to use the same query information. However, now we're going to use an Earth observation job configuration, and we're going to be creating our own index. This is the vegetation index where we subtract the red band from the near IR, and then we normalize that by dividing by the addition of the near IR and the red band. Okay, so we create this job. Now we want to kick off the job. We kick off the job and we can see that it's initializing. This is going to take a little bit of time to complete. So we'll go ahead and create this waiter function that's just going to wait and check the status of the Earth observation jobs. And we can see that this example takes about 20 minutes to complete. So it took about a minute to initialize and then about 19 minutes to complete. And that's on those 25 images that meet the requirements that we started with. We can go ahead and visualize the Earth observation job outputs and inputs, and we can use the geospatial mapping capabilities that are part of SageMaker Geospatial. Here I'm going to render this information using the map. So I'm overlaying the true color image, the vegetation index, and the area of interest here. So you can see the red box, or the dark black box is the area of interest. That's where I want to calculate the deforestation that's taking place. The normalized vegetation index is overlaid on it. And these dark red areas are near -1. The lighter regions are near +1. So much heavier vegetation near the lighter areas. And we can also use our mapping tools here to change the layers. So maybe we want to put, the area of interest actually behind the vegetation index. We can do that and interact with our data in real time. So quite powerful. So good to be able to visualize it. We can also visualize the output of our Earth observation job without downloading all of the data. Here we're visualizing it using that capability in the notebook. Okay, so we've visualized our data. I now want to extract the results. We visualized it, but we didn't extract it yet. So that's what I'm going to do next, where we extract this information to an S3 bucket.
Hey, Aaron, why do you need to extract these results in S3?
Yeah, good question. So if you're used to using SageMaker for other machine learning applications for building, training, and deploying, many times we use S3 as a conduit between a processing job and a training job or deployment job. We're going to do the same with SageMaker Geospatial. However, many times you want to chain operations together. So we might want to first do a cloud masking operation, and then we do a band math operation, and then we do a resampling operation, and then we export it. And we don't need to export those intermediate stages. So here we're going to call export at the very end, just to dump those results into an S3 bucket.
Oh, this is a nice way to save me some storage.
Yeah, it saves you storage, and then you have a consolidated location where the results are stored. Okay, so we'll export the data. I've created a waiting function again for that export. The export's much faster than the Earth observation job. So this only takes about 5 minutes to complete, and we can see it took a total of 364 seconds. Okay, so we've processed our data. We've selected our data. We've processed our data. Now we've exported it. Now let's calculate the vegetation index. We've already calculated the index. We want to calculate the area that we're interested in. So to do that, I actually need to download that data from the S3 bucket to the Elastic file system that's supporting my SageMaker Studio domain. So now I'm going to download the data.
Aaron, so you have mentioned you have already exported this result into S3. Why do you need to download all this data again to an EFS?
Yeah, good call out. So the data lives in S3 right now. We've exported it.
Right.
But I need to read the data into memory. I want to do math on this data. I need to threshold and calculate the total area. So to do that, I can't do it when it's resident in S3. I need to download it to the Elastic file system that's supporting the SageMaker Studio domain so I can interact with it.
Makes sense. Thank you.
Yeah, and that's what I'm going to do next. So I just downloaded not only the masks, but also the raw images. And I'm downloading that to the Elastic file system, the EFS that's supporting this. And you can see those are going to be stored in images and mask folders here. Now we're going to extract that area of vegetation. And to do that, I'm going to use a threshold of 0.4. Actually, in the academic literature, there's some debate on where the exact threshold is for very dense packed forest. We're going to use 0.4. We have a link here that has a couple of suggestions for thresholds to use. So anything greater than 0.4 for this vegetation index, we're going to consider that as dense forest. And then we're going to calculate the area. Because we know these pixels are 10 meters by 10 meters, we can calculate for every pixel that is at index greater than 0.4, that contributes to the total area of dense vegetation. Okay, so we're going to loop over all of our images and do that. And what we produce here, let me just show you this, is a single image. So on the left-hand side, let me just walk you through this. On the left-hand side, we're showing the true color image. And you can see, again, this dense forest area in the dark green. Now we've thresholded it on the right-hand side. We're looking at the vegetation mask on the right-hand side. So anything in green is a value greater than 0.4. Anything in red is less than 0.4. So again, vegetation is in the green. We can see the date here. This is May 31st, 2022. And the total area that we calculated for this image is 9,618 square kilometers. So from this vegetation index alone, knowing the spatial resolution, we can actually calculate the exact area of vegetated land in this image. Really powerful analysis to get it by location and by time. So we can see how this changes over time. And that's what we're going to do next. Let's see how this changes over time. We're going to split out the analysis into 2020, 2021, and 2022. So we can extract that area and we can plot it actually to see that for this location in Brazil, here in the blue line is 2020, the orange line is 2021, and the green line is 2022. Now we're plotting here against, on the x-axis, time. So we see months of June, July, and August. And we can see that there's already seasonal variability that we would expect, right? As we start from the spring and approach fall, that we see the amount of vegetation decrease. That's expected. And that's the overall trend of these curves. However, we see these curves reduced over time. They are going down in total vegetation area. So we can see that 2021 had less vegetation than 2020. 2022 has less vegetation than 2021 and 2020. So very powerful analysis using geospatial data. You might notice here too that not all of the dots are filled in consistently. And the reason for that is that we had a cloud filter, right? So we might have images at these dates that were acquired in 2022. However, the cloud filter was too great, right? This could be occluded by clouds and we wouldn't be able to do our analysis using that visual red band and the near IR. Lastly, I'm just going to animate 3 different images as a function of time. So we're going to create this animation. These are just 3 images separated by a single second. If you look up here at the date, it's going to progress between 2020, 2021, and 2022. This is for the same exact date of July 5th on each one of those years. And you can see over time as we progress, the red area is growing, right? This validates what we showed in that time series plot, that the vegetation index, the total vegetated area of dense forest, is decreasing over time. All right, so we showed you, just to recap, how to query the data from Sentinel-2. That was not only by location, but also by time and cloud filter. We showed you how to create an Earth observation job for that custom band math operation to calculate the normalized vegetation index, how to export the data, and how to read it into memory from our Elastic file system so we can do downstream analysis, visualization, and overlays like you're seeing here on the screen. Any questions from the chat? All right. We will work to answer the questions in the chat. If there are no other questions, let's shift gears here over to Zhang to get started on the geospatial analysis for glacier coverage on Mount Shasta in California. Take it away, Zhang.
Thank you, Aaron. Aaron just showed you how you can use band mass to track deforestation happened in Brazil. So in this example, we will show you something different. We will be using a deep learning model to track the glacier melting happened in the Mountain Shasta, California. So in this demo, we will show you how you can monitor this glacier melting in Mountain Shasta using a pre-trained model provided by SageMaker Geospatial. Here's the outline I will follow in this demo. We will start by setting up the environment for running these SageMaker Geospatial capabilities. And then we will use SageMaker Geospatial capability to query the Sentinel-2 data for analysis. Once we acquire the data, we will then, using this pre-trained model, to identify the glacier in Mountain Shasta and visualize the results in Foursquare Studio. Next, we will extract this snow coverage and measure the actual area covered by snow and ice. At last, we will analyze the relationship between the snow coverage and the surface temperature that is derived from another satellite called Landsat 8. So this is the standard way you set up an AWS service. We need to do is to start a Boto 3 session and create a SageMaker client using this service name, SageMaker Geospatial. Now we have the SageMaker Geospatial ready. The next thing to do is get the data, as always the first step of your machine learning journey. Luckily, SageMaker Geospatial makes this data query really, really easy. All we require to do is the location of the data, time frame of the data, and filters that you want to use to refine your data. So for the location of the data, we will define an area of interest, which can be specified as a polygon. And these numbers are the coordinates, latitude and longitude coordinates of your polygon vertices. And we are interested to see the snow coverage change in the past 5 years. So we would query data from 2017 to 2022. And one common challenge is when working with satellite data is cloud. As you can see in this example, clouds may sometimes get in the way. It will cover the area you want to analysis. This is a picture over the mountain Shasta. You barely can see the snow mountain, but on the left-hand side is a clear image where you don't have any clouds. So we definitely want to use image on the left-hand side rather than the images on the right-hand side. So to do that, we will set the cloud coverage upper bound to 1% so that we can get all the clear images.
Is there any reason, Zhang, for putting it for anything other than 1%? I use that same filter on my example. I see you're using it on yours. Should we do that for every type of analysis with geospatial data?
Great question. Actually, yes, there are some analysis you don't want to filter out all the clouds because some studies, it's just you want to analyze the cloud itself. Clouds can give you very useful information for you to do weather forecasting and weather warnings. Like additionally, sometimes you may have clouds that cover the image, but not necessarily cover the area you're interested in. This cloud coverage filter are looking at the cloud for the entire image, not necessarily the area of interest you define. So even you may have some clouds like the second image in this plot, you have some clouds scattered around the image, but you can still see the snow mountain. So that would be a valid image for you to still run the analysis.
Got it. Okay, thanks.
Sure. So we just run this data query. We find out there are 163 images in the past 5 years over the mountain Shasta area. We will be using these images to analyze the snow cover changes.
Zhang, I see you have 163 images in your request. How do you take that and then go and determine where is the glacier in the image? What's the next step?
Great question. SageMaker Geospatial offers a land cover segmentation model, which can classify each pixel within the image into a common land cover type, such as vegetation, bare land, water, snow, and ice. In this example, we will use the snow and ice to estimate the glacier area in Mountain Shasta. Here's an example of the land cover segmentation output over the Seattle area. The land cover type is indicated by different colors. We will be looking for this dark green color that represents the snow and ice. So if you look closely to the lower right corner of this image, this is actually the mountain rainier in the Seattle area. If you look at the land cover mask, you will see this snow mountain are actually marked as dark green. Cool. So we will be using this land cover segmentation model to find the snowpack in Mountain Shasta. Using this land cover segmentation model is really easy in SageMaker Geospatial. All we require to do is specify two configurations. One for the input data, one for selecting the model we want to use. For the input data, we will be using the same query we use to get the data. So the same location defined by area of interest, the same time range filter to find the data from the last 5 years, and also using the same cloud coverage filter to get the clean images. So for the job configuration, we will just use this string to select the land cover segmentation model we want to use.
Is that the only operation that's available? I mean, I guess I showed band math in my example, but how do we know what operations are available to us?
Yeah, SageMaker Geospatial now actually support both data processing and machine learning models. All these supported operations are listed in the developer guide. As you can see from here, we have more than 10 types of operations supported in SageMaker Geospatial today. So you have things like cloud masking, where a deep learning model will help you mask out all the cloudy pixels within your satellite images, or geomosaic, which will take multiple smaller images and stitch them together as a bigger one. Or you can also do zonal statistic, where you provide a polygon or a bounding box, and the processing will help you calculate the statistic within the area you define. So there are multiple operations supported in SageMaker Geospatial today.
Cool. And for those deep learning ones, do we have to train those, or those are already trained for us?
This is pre-trained model you can use out of the box.
Cool.
So we just kick off this job, and we can use this get Earth observation job to monitor the job status. As you can see, I just launched the job. It's already in progress. And let's take a moment to talk about the duration of the job that we just launched. It is expected to take about 1 hour to finish this job. Remember, we have 163 big images. This 1 hour may seem a long time. However, it is important to understand the work SageMaker is doing behind the scenes. Like for comparison, I want to share an example of a similar task that I completed on my own. Downloading all the spectral bands from Sentinel-2 and assemble them as a multispectral image will take me 1 minute using this studio notebook. So if you are processing 163 images, that's already more than 2 hours, or close to even 3 hours. But with SageMaker Geospatial, you can finish everything in 1 hour. So SageMaker Geospatial not only pulling all this data, it also processes them to make sure that it can be used for model inference. Once the model runs through the data, you will save the results into S3, making it easy, accessible for further analysis. Considering the scope and the complexity of the work being done here, the efficiency of SageMaker Geospatial is quite impressive. So once the job is marked as done, we can visualize the results using the integrated Foursquare Studio, which is an interactive map you can use within the notebook itself. So since the job we just launched will take an hour to finish, I will pick a job I run before this learning session. Here, I can initialize a map object using SageMaker Geospatial map. And here's this colorful image on the screen is the line cover segmentation map over the mountain Shasta area.
How do we know though that that's Mount Shasta? Like, how do we verify that?
Great question. This interactive map gives us a lot of options to directly work on the layers. So if we want to verify whether this dark green really aligns with the mountain Shasta, one thing we can do is change the opacity of the line cover mask or transparency of this layer. When I gradually decrease the opacity of the layer, you can see whether that dark green color aligns well with the underlying snow mountain. As you can see, this dark color is in the center of the screen. If I reduce the opacity of the land cover mask to 0, you will see the underlying satellite image.
This is great.
In this case, yes, you can see the model actually captures the snowpack in Mountain Shasta. Now that we have verified the results, we can move on to exporting the land cover mask to compute the snow cover area. I will export the results. The way we manage this data is using ARN. A big benefit of this is you don't need to download all the data. You can organize your output using the job org so that can be easily shared across your team. Here I exported results to my S3 bucket. I can also monitor the export job the same way I monitor the Earth observation job for model inference. So once I have downloaded all these images to my local instance, I can start to compute the snow coverage. As you can see, all these results are saved in TIFF format. Actually, SageMaker Geospatial's default output for this line cover mask is cloud-optimized GeoTIFF. This GeoTIFF file that contains spatial reference information, meaning you can actually overlay them onto a map. You will see not only the mountain itself, you will also see where it's located on the Earth's surface. So here I will run this cell to compute the snow coverage in Mountain Shasta. So this land cover segmentation mask classify each pixel into a common land cover types, and each pixel within the land cover mask has an index between 0 and 11, and the snow and the ice class has an index 11. So we can extract a snow mask by ignoring all the other classes. So here we extract the snow mask. Now we can move on to compute the actual area covered by snow. Here we count the number of pixels marked as snow and multiply that with the area covered by each pixel. Here's a little bit different than what Aaron showed in the deforestation example, because that example using the RGB, using the red band and the near infrared band, where you have 10-meter resolution. But for land cover segmentation model, because there are various resolution in Sentinel-2 bands, and this model downsampled the area bands to 60 meter to run the inference. So each pixel covers a 60 meter by 60 meter area, and they divide 1,000 by 1,000. We will convert this area into square kilometer. Here, I compute the snow area over the last 5 years, and we will extract these results. We will check in the first week of July. Plotting the snow area as a function of time, we can see a clear downward trend from 2017 to 2019. The snow coverage area decreased from 78 square kilometer to 13 square kilometer over 5 years. However, we noticed there's a spike in 2019. To confirm whether this spike is an actual increase in snow cover or an error from the model inference, we will overlay this snow mask with the actual Sentinel-2 image. Here's an animation of the snow coverage changes over the past 5 years. Snow and ice are marked as red. Interestingly, we can see in 2019, we do see a big increase in snow coverage. So this verifies our result. This is not an error in the model inference. It's actually happened. We have more snows in 2019.
This animation is amazing, Jung. This is great. I like that we can see the outlier in 2019, and I expect that seasonal effects will still be present here. Are there other data sources, though, that we can use to validate this as well? Like this was using the visual bands with a segmentation model. Is there any additional analysis that we can do to verify this?
Absolutely. We always want to cross-check our result to make sure this is not some error or bias happened in our analysis. So for that, we will use another satellite called Landsat-A to track the surface temperature changes over the same area in the last 5 years. So here we will query the Landsat-A data the same way we query Sentinel-2. We will be using the same exact area of interest, the same time frame, And the same cloud coverage. Here's a little bit different. So we will be using a band called LWIR11. This LWIR stands for long wave infrared, which is the 11th item that is stated in this dataset product. So we will run the query to see what are the data available in Mountain Shasta. You can see we have a lot of images that it captures in the last 5 years.
And Zhang, just to make sure I'm clear, the long wave IR, that's measuring what again? I know that's a spectral band, but what are we trying to get out of it?
Good question. This is a satellite called Landsat 8. It actually used to measure the land cover over the globe, but there are some special bands you can actually use to measure the surface temperature. So this Landsat satellite uses a sensor called thermal infrared sensor to measure the surface temperature. This surface temperature instrument has two bands that are sensitive to thermal radiation, one centered at 10.9 micrometers and the other at 12.0 micrometers. So the amount of thermal radiation emitted by a surface is directly related to its temperature. So if you can measure the amount of thermal radiation emitted by that surface, you will be able to compute the temperature of that surface. This is what Landsat 8 does.
Got it. Cool, thanks.
So we download all this Landsat surface temperature data, and we will compute the Earth's surface temperature. In this way, here we first do a crop, and then we follow this equation to get a surface temperature for the Mountain Shasta.
Now that equation looks kind of complicated. How did you come up with that?
Yes, this is actually indicated by the Landsat Level 2 collection to science product. This will tell you how you can actually compute the surface temperature from this product. So it has a scale factor as 0.00341802. It also has an additional offset of 149. So using these two scale factors, you will be able to convert the product into temperature measured in Kelvin. For us to see in a normal day unit, we want to convert them into Celsius. So that's where the minus 273 is for.
Got it. Okay.
So we use this equation to convert the surface temperature into Celsius. Here we compute all the results. By deriving this surface temperature from Landsat 8 data, we now can investigate the relationship between snow coverage and the surface temperature. One way to measure this relationship is by calculating the Pierce correlation coefficient, which quantifies the linear relationship between two variables. The coefficient ranges from -1 to 1, with 0 indicating no correlation at all, and a +1 and a -1 indicating a perfect linear relationship. As you can see, the snow coverage and the surface temperature has a -0.95 Pearson correlation coefficients, which means these two variables are almost perfectly negative correlated. This suggests that as the surface temperature increases, the snow cover area tends to decrease and vice versa. Now let's plot out these two variables as a function of time. As you can see, we observe a clear downward trend in snow cover area, which is the blue curve in this plot, and the red curve is the surface temperature on Mountain Shasta over the past 5 years, where we see a clear upward trend. By analyzing these trends, we can now confidently say the peak in 2019 is not an outlier. It's not an error from the model, as we see a corresponding dip in the surface temperature at the same time. Yeah, that's a wrap of the demonstration for SageMaker geospatial capabilities. We hope you found this example we present today on monitoring the glacier melting at Mountain Shasta informative. By leveraging the power of satellite data and machine learning, we were able to identify these mountain glacier changes and derive the surface temperature. If you would like to explore more or try out the demo yourself, you can find our notebook in Amazon SageMaker examples repository. Additionally, we encourage you to use these tools and the features we developed in SageMaker Geospatial to build your own geospatial applications.
All right, so we've shown you today how to get started with SageMaker Geospatial. We've shown a demo on deforestation, how we can monitor deforestation using not only the visual band, such as the red band and the near IR band, looking at the vegetation index. We've shown how that changes over time, how we can monitor that from space using data sets available in SageMaker Geospatial today. We also showed how to monitor the snowpack glacial coverage of Mount Shasta in California. For that analysis, we used both land segmentation models and thermal analysis to determine the temperature of the Earth's surface. To get started today, here's some links for the official website and the announcements around SageMaker Geospatial, the developer guide, and these notebooks are available for you to use today. These are available as part of our SageMaker Examples GitHub, and there's a number of different geospatial analysis that you can get started with today. We want to thank you for joining SageMaker Fridays, where we could do a deep dive on SageMaker Geospatial capabilities. We hope you learned something today, and I can't wait to see what you build with the geospatial capabilities that are now available in SageMaker.